Today we are going to learn hydrogen and hydrogen-like atoms. Hydrogen and hydrogen-like atoms. The quantum mechanical treatment of hydrogen atom or hydrogen-like atoms. You know what is the composition of the hydrogen atom? What are the constituent particles of the hydrogen atom? Hydrogen atom has a nucleus, and the nucleus contains a proton. And the proton has the charge plus E, okay, where E is the charge of the electron or charge of the proton, and the nucleus has the charge plus E. And there is an electron around this nucleus, and the charge of this electron, the electron is here. This is a simple Bohr model, but that is not the model that we are going to establish after this quantum mechanical treatment. But this electron has a charge minus E. So this is a very simple system, a two-particle system. The two-particle system is the electron, the system which consists of the electron and the nucleus, okay. And this is a very simple system. And we can also talk about the hydrogen-like atoms. For example, helium plus. And in this case, how many electrons are there? Helium has 2 electrons, and if one of the electron is striked out, then helium has only 1 electron, that is helium plus. And it has 2 positive charges in the nucleus. So the nucleus has plus 2e as the charge, and around this nucleus there will be one electron with the charge minus E. And what about Li2 plus? Lithium has 3 electrons, and if 2 electrons are kicked out, then it will have only 1 electron remaining. Then in that case it has a nucleus with 3 positive charges. 3 plus 3e is the charge of the nucleus, and around that nucleus there will be an electron with the charge minus E. See, all these systems are two-particle systems. Here, if it is a hydrogen atom itself, it's a two-particle system of a nucleus of plus E charge and an electron around it. And these are hydrogen-like atoms. And here there is these systems are also two-particle system, and the nucleus of this one has plus 2e charge, and around the nucleus, that is the first particle, there is another particle called electron, okay, and this has 3 positive charges plus 3e, and around that particle there is an electron of charge minus E. So all these are two-particle systems, and these type of systems are called hydrogen-like atoms. So in general, a hydrogen-like atom is an atom which has a charge of plus Ze plus Zd, where Z is the atomic number, and around that there is 1 electron, okay. Around that there are not Z electrons, but there is only 1 electron. So any system of this kind is called hydrogen-like atom. We are going to learn the quantum mechanical treatment of this type of atoms, hydrogen-like atoms, or this type of systems. And the quantum mechanical treatment of this type of system is simple, or the Schrodinger wave equation is exactly solvable, especially because it is a two-particle system. Since it is a two-particle system, there will be an attractive potential energy between the nucleus and the electron. Okay, there is only one type of interaction, that is the nucleus electron attractive energy. If there were more than one electron, there would be more than one type of interaction, like electron repulsion, the first electron nucleus attraction, second electron nucleus attraction, like that. There will be more than one interactive terms. But in our case, there is only one interaction, and that is why the Schrodinger wave equation is exactly solvable. Okay, and we will learn how to solve the Schrodinger wave equation of this type of system. The attractive potential energy in this case, the attractive potential, we represent potential energy as V. So V is equal to minus Z E square divided by 4 pi epsilon 0 R. This is the potential energy due to attraction between the charge plus ZD and minus E. And the 4 pi epsilon 0, the term 4 pi epsilon 0, this one appear here because we are expressing this in SI units. Okay, so this is the potential energy of the system. So we can easily constitute the Hamiltonian for this system. The Hamiltonian in this case, H cap, is equal to, what is Hamiltonian? That is a total energy operator, that is the kinetic energy operator plus the potential energy operator. Kinetic energy operator plus potential energy operator. And here, kinetic energy operator, what is the kinetic energy operator? Whether we are considering the kinetic energy of the nucleus or the kinetic energy of the electron, because we are considering a two particle system. So kinetic energy, the total kinetic energy is nothing but the kinetic energy of the nucleus and the kinetic energy of the electron. So we can write it as T cap N, that is a kinetic energy operator for the nucleus, plus T cap E, that is a kinetic energy operator for the electron, plus the potential energy operator V cap. Okay, and the kinetic energy of the nucleus. What is the kinetic energy of the nucleus? The kinetic energy of the nucleus means nucleus is in motion. Actually, it represents the translational motion of the atom, right? The nucleus is in motion means the atom as a whole is in motion in the space. There is a relative change in the position of the atom in the space. Then only we can say that the nucleus is having some kinetic energy. But this kinetic energy, that is the kinetic energy of the nucleus or the movement of the nucleus, has nothing to do with the internal structure of the atom. The internal structure of the atom is nothing but how the electron is distributed around the nucleus. So the nucleus is moving, or the atom as a whole is moving, that has nothing to do with the internal structure of the atom. So that is not important for us. So we are not including this term in our Hamiltonian because that is not going to deduce some useful information in our case regarding the structure of the atom. So we are talking about the kinetic energy of the electron, because the kinetic energy of the electron is due to the motion of the electron, and the motion of the electron is very important because the motion of the electron is going to determine in which place or which position around the nucleus there is a probability to find the electron, right? That is going to define the structure of the atom. So that is only important for us when we are going to study the structure of the atom. So in quantum mechanics, by solving the Schrodinger wave equation, we are going to understand what is the internal structure of the atom. By saying internal structure of the atom, what we mean is that how the electron is distributed around the nucleus. Okay, so our Hamiltonian will be the kinetic energy operator for the electron plus the potential energy due to the attraction between the nucleus and the electron. So the Hamiltonian in our case, H cap is equal to minus H square divided by 8 pi square m del square, that is the kinetic energy part del square, plus the potential energy part V cap. You may be remembering that in our previous system that we have studied so far, we put the potential energy as 0. We were assuming that the particle that we were considering is not under the influence of any external force. So there the potential energy term V cap was 0, and therefore the solving the Schrodinger equation was pretty simple. In our case, we are dealing a real system. Here the potential energy cannot be considered as 0. There is a potential energy due to the attraction between the positively charged nucleus and the negatively charged electron. So in this case, apart from the case of the particle in a ring or the particle on the surface of a sphere, in this case we have a real potential energy term. Okay, and the Hamiltonian is minus h square divided by 8 pi square m del square plus v cap, and here the del square represents the del square represents, del square what it is, dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and the x, y and z are the position coordinates of the electron. Okay, so this del square is for the electron, and what we have to do here is that we have to express this del square in terms of polar coordinates. We already learned previously how to express del square in terms of polar coordinates. So in our case, the Hamiltonian will be minus h square divided by 8 pi square m. What is del square in polar coordinates? 1 by r square dou by dou r of r square dou by dou r plus 1 by r square sine theta dou by dou theta of sine theta dou by dou theta plus 1 by r square sine square theta dou square by dou phi square. That is del square in terms of polar coordinates. And now we have the kinetic energy part of the Hamiltonian plus the potential energy part. Potential energy operator is nothing but minus z square divided by 4 pi epsilon 0 r minus z square divided by 4 pi epsilon 0 r. Now we have the Hamiltonian for the hydrogen-like atoms. Okay, and now we can constitute the Schrodinger wave equation. The Schrodinger wave equation is h cap psi is equal to E psi. This is the Schrodinger wave equation, and we already know what is h cap. Therefore, we can make the Schrodinger equation here. So our Schrodinger equation is minus h square divided by 8 pi square m 1 by r square dou by dou r of r square dou psi by dou r plus 1 by r square sine theta dou by dou theta of sine theta dou psi by dou theta plus 1 by r square sine square theta dou square psi divided by dou phi square minus z square divided by 4 pi epsilon 0 r into psi. Now it is h cap psi. This is the kinetic energy part of the Hamiltonian. This is potential energy part. Both part has been operated over the function psi. So that is why we have put psi here. Dou psi by dou r, dou psi by dou theta, dou square psi by dou phi square. Okay, and the potential energy part also operates over psi. That is why it is minus z square by 4 pi epsilon 0 r into psi is equal to E psi. That is the right hand side of the Schrodinger wave equation. Now we have the Schrodinger wave equation here, and what we are going to do now is that we are going to express psi as a product of three independent functions, because psi is a function of both. Psi is a function of r theta and phi. R theta and phi are the coordinates that we are expressing the polar coordinates, right? So psi is the wave function corresponding to the electron, and the electron can be anywhere around the nucleus. Therefore, there is a range of r values possible for the electron. Apart from the case of the particle in a ring or particle on a sphere, the r is a variable here. In the case of particle in a ring, r was fixed. In the case of particle on a sphere also, r was fixed because it was moving over a ring or sphere of constant radius. But that is not our case here. Our electron is not confined to an orbit like this. Even if I have drawn like this, in quantum mechanics we are not going to assign an orbit or circular path for the electron. Our assumption is that electron can be anywhere around the nucleus. Therefore, there is no fixed r here. Therefore, you can consider an atom of concentric spheres. So many spheres are stacked together. Okay, the spheres of so many radius are stacked together, and that is how an atom look like. Therefore, you have r as a variable here. So psi is a function of r, theta and phi. Therefore, psi can be expressed as the product of three functions. The first function is r, capital R, and that capital R is a function of r. Then p, which is a function of theta, and f, which is a function of phi. You know this kind of mathematical operation because we have already learned this kind of steps while learning the particle on a sphere. Okay, so psi is r p f, or we can write simply r p f. So wherever you find r, it means that it is r of r, or p means p of theta and f means f of phi. Okay, or f is a function of phi, like that. So psi can be expressed as the product of these three functions. So now let us operate, let's expand this Schrodinger wave equation for the hydrogen atom by substituting for psi that psi is equal to rpf. Then we will get a Schrodinger wave equation minus h square divided by 8 pi square m 1 by r square dou by dou r of r square dou psi by dou r, where psi is substituted with the r, p and f. Then the dou by dou r will operate only over r, and we can take p and f out, right? So we get p into f into 1 by r square d by dr of r square dr by dr. Here I have put the symbol for the total differentiation, because the symbol for partial differentiation is no more required, because we are differentiating this function with respect to only one function, having only one function defined by one variable. R is a function of r only, the small r only. Therefore, we don't need to use the symbol for partial differentiation here. We can take the symbol of the total differentiation itself. So that is minus h square divided by 8 pi square m p into f into, in this case p and f will be taken out, because it is the differentiation is not going to operate over these functions, because these functions are not the functions of r. The differentiation is with respect to r, it will operate only over r of r. So that is why we have put pf 1 by r square d by dr of r square dr by dr plus next term, that is the differentiation with respect to theta. So it will operate only over p, because p is a function of theta. So we can take r and f out, because I is rpf, r and f will be taken out. So we can write rf 1 by r square sin theta d by d theta of sin theta dp by d theta, like that. Next term is the differentiation with respect to phi, so it will operate only over f of phi. So we can write r into p into 1 by r square sin square theta d square f divided by d phi square, okay, minus z e square divided by 4 pi epsilon 0 R into psi is equal to R P F is equal to E into R P F. Okay, so we have substituted RPF for psi. And what we can do next is that we can bring this term, the term on the right hand side to the left hand side. So our equation will be similar. So we will get the equation like minus h square divided by 8 pi square m into p into f into 1 by r square d by dr of r square dr by dr plus r into f into 1 by r square sin theta d by d theta of sin theta dp by d theta plus r into p into 1 by r square sin square theta d square f divided by d phi square. Okay, now I am going to bring this the term in the right hand side to the left hand side, so that we will get z 8 pi square m by h square. We will multiply this with this one later, so that we will get minus of z e square divided by 4 pi epsilon 0 r plus e into r p f is equal to 0. What we have done is that we brought this here so that it will be minus e rpf. We already have minus z d square by 4 pi epsilon 0 rpf. So rpf is a common factor, minus rpf. Okay, minus is also common factor in both terms. Then we get minus of z d square by 4 pi epsilon 0 r plus e into rpf is equal to 0. Next, what we are going to do is I am going to multiply this equation with minus 8 pi square m by h square, minus 8 pi square m by h square. So multiply with minus 8 pi square m divided by h square. I am going to multiply this equation. So what I will get? Minus 8 pi square m by h square. So this minus h square by 8 pi square m is common for this term and this term up to here, from where the square bracket begins and to where the square bracket ends. Okay, so from this and there are three terms, the minus h square divided by 8 pi square m will be cancelled when I am multiplying this with minus 8 pi square m by h square. So this term will be cancelled, this h square divided by 8 pi square m, this term. So what we are going to get is p into f into okay 1 by r square d by dr of 1 by r square d by dr of r square dr by dr, that is this one, r square dr by dr plus r into f into plus r into f into 1 by r square sin theta d by d theta sin theta dp by d theta, 1 by r square sin theta d by d theta of sin theta dp by d theta, d by d theta of sin theta dp by d theta. Then next term plus r into p plus r into p into 1 by r square sin square theta, 1 by r square sin square theta d square f divided by d phi square, d square f divided by d phi square. So up to that minus h square by 8 pi square m was a common factor, so this term has been cancelled by multiplying with this one. and then we have to multiply the other term, this term, with minus 8 pi square m by h square. So we get plus, because there is already a minus sign here, so plus 8 pi square m by h square into z e square by 4 pi epsilon 0 r, z e square divided by 4 pi epsilon 0 r plus e, right, into rpf is equal to 0. 0 when multiplied with this one, it's 0. Okay, so now we have multiplied this with the minus 8 pi square by h square. We can again simplify this term by multiplying with, multiply with r square sine square theta, divided by rpf. You can note why I multiplied this with r square sine square theta divided by rpf, because you can check this, all these terms are mixed now. See, this is a function of p, f and r, r, f, p, here r, p, f. So the functions are mixed. I want to separate the functions. So what I am going to do here is that I am going to multiply this with the r square sine square theta. R square sine square theta is the denominator of this term. See, r square sine square theta. Then I am going to divide all the term with the rpf, so that I can separate the variables. Okay, I can separate them. At least in some terms the variables will be separated. We can check it how it is coming. So let us take the first term, pf by rpf. So it will be, p and f will be cancelled, so what is remaining is 1 divided by r into what is in the r square and r square. R square is there in the denominator, this one is r square, and this r square will be cancelled, so what is remaining is sine square theta. So sine square theta, then d by dr of r square dr by dr, okay, plus r divided by rpf. So r and f will be cancelled, so what is remaining is 1 by p into r square, and r square will be cancelled. Sin theta in this denominator will be cancelled, 1 over the sin theta in the numerator. So what is remaining is sin theta, okay. So sin theta by p, then d by d theta of sin theta dp by d theta plus r into p divided by rpf. So what is remaining is 1 divided by f into r square sine square theta, and r square sine square theta will be completely cancelled. So what is remaining is d square f divided by d phi square, plus now we have to multiply with this also, r square sine square theta by rpf. So here 8 pi square m by h square into z d square divided by 4 pi epsilon 0 r plus e into, now we are going to multiply with this one, okay, a r square sine square theta by rpf. So rpf and rpf will be cancelled, and what is remaining is r square sine square theta, that is equal to 0. So now look at this equation. The first term in this equation is a function of r and theta. Both r and theta are there, so there are mixed variables. Then the second term is a function of p alone, and the third one is a function of f alone, and the fourth one is a function of both r and theta. So what I am going to do is that I am going to take now the theta and f terms are mixed. Okay, theta and r terms are mixed. Here r and theta are there. Okay, here only theta is there, but here r and theta are mixed. So only one of the variables, that is a phi, is having an independent term here, or an individual term here. So I'm going to take this phi term to the right hand side of the equation. So the equation will be 1 by r into sine square theta into d by dr of r square dr by dr plus 1 by p sine theta d by d theta of sine theta dp by d theta, okay, plus 8 pi square divided by h square into z e square by 4 pi epsilon 0 r plus e into r square sine square theta is equal to minus 1 by f d square f divided by d phi square. Okay, see, the right hand side is a function of f only, or phi only, and the left hand side is not a function of phi. The left hand side depends upon r and theta only. You know this type of situations, right, when you are learning the particle in a sphere. And in this case, this is possible only if the both sides is equal to a constant, and let us take that constant as m square. Okay, m square is the constant. Now the video is already more than 30 minutes. I will stop this video here and explain the rest of the stuff in the next video.